So my name is Greg Antel, and I'm a machine learning architect and product manager here at BigML, and excited to share with you principal component analysis. I'd first like to go over a brief agenda about what I'll be discussing in the next half an hour or so. The first thing we're going to be doing is talking about the utility of PCA, or principal component analysis, overall in machine learning workflows, when and why you should use them. We'll be talking about some of the challenges posed by high-dimensional data in machine learning applications and why PCA is useful to combat them. We'll be talking about the intuition and methodology behind PCA a little bit, and then we'll show a use case using a BigML dashboard. And then finally, we'll talk about some of the unique specific implementation aspects of BigML's PCA. So I'd like to first start by covering its utility in a high-level machine learning workflow. So if you think about an overall machine learning application, there's a number of tasks that you'll run through, beginning with problem formulation, running through data acquisition and data transformations and feature engineering, and then ultimately ending up with your model and the predictions of the model and the results that you can measure and how well that model is performing. So throughout this process, there are a number of checkpoints where essentially you might want to go back and change certain things. And very often, it's more common to change the model rather than changing models. Improvement more often comes from collecting more data or engineering more features or better features for your model. And this is basically the garbage in, garbage out principle of machine learning. If you don't have good data or good representation of your data before you start a machine learning task, you're not really guaranteed to get useful results out of it. Another reason why it's often a better investment of time to go back to the feature engineering or data acquisition steps is because model training and hyperparameter tuning can now essentially be automated with things like Optimal on the BigML platform, whereas machine learning and feature engineering cannot be really automated. So feature engineering is still very much an art in a lot of aspects. So today's release now further expands what's possible in BigML, specifically for this data transformations feature engineering step of the process. Our previous release was on data transformations more in general, and this adds another layer of sophistication to what's possible to do in the BigML platform. So I want to talk now about what are some of the problems of high-dimensional data in machine learning and why PCA is useful to combat this. So what do I mean by high-dimensional data? Typically, when you talk about the machine learning ready format of a data set that's structured into rows and columns, where your rows are your instances or your observations or examples of your data set, and your columns are your features or your fields or your variables. So these words can be used fairly interchangeably, and I might refer to them by different names throughout the presentation. So typically machine learning performs better when the number of instances you have is much larger than the number of features, but not all data sets come in that format. You can end up with what's sometimes referred to as wide data or high dimensional data, where you have a large number of fields with very few instances. A common example of this might be in biological data or maybe like stock market data, where you can record lots of different variables and it's fairly cheap to acquire all of that data, but maybe there's not a ton of different instances. There's only so many companies in the world, or there's only so many individual patients that you can collect data from. Why is this high-dimensional data dangerous? Well, it implicitly will increase the model complexity. By introducing more variables to your modeling process, you become very prone to overfitting automatically by virtue of having more parameters in your model. And so in order to combat this, one way is to require more observations. But that's not always possible, especially with a fixed size of your data set. High-dimensional data will also contain correlated variables very often, or sometimes useless variables. And these are things that aren't useful for your model. High-dimensional data is also very difficult to visualize typically. Anything beyond 3 dimensions really is quite difficult to visualize in a very simple manner. And when you get to hundreds or thousands of variables, it becomes an even bigger hardship. And then finally, high-dimensional data can take a long time to train models or make predictions. And again, this has to do with the added number of parameters in your model. Fortunately, principal component analysis addresses all of these issues in different ways. It doesn't You might not necessarily use principal component analysis to address all of these issues in the same task, but you might choose, it might be useful for you for a subset of these different challenges depending on your application. And so I referred to model complexity a few times in terms of adding parameters to your model increases model complexity. Why this is important is because models that have lower complexity can also be very advantageous. And so if we're going to talk about dealing with high-dimensional data, we might want to lower the complexity of the models that we're dealing with. So for example here, I have a plot on the left of the performance of a model or its test error as a function of the number of training examples. So we can imagine a low complexity model in blue and a high complexity model in red. And holding all things constant, as we increase the number of training examples, eventually models with lower complexity will converge to a higher test error rate than our more complex models. But you can see here there's a certain threshold that exists where not enough training data is actually available to favor the more complex model. So for situations where you have a fixed amount of data or not a ton of data to work with, a less complex model is often more favorable in those situations. So there's lots of ways we can bat high dimensional data and simplify our models. A lot of these deal at the model level with regularization techniques. So for a simple decision tree model, we might use pruning or limiting node thresholds in our models. For ensemble techniques, there's regularization techniques such as bagging and randomization that are introduced. For logistic regressions, we can introduce L1 and L2 penalties to our cost function, and for deep nets or neural networks, we can use things like dropout to deal with high dimensional data. But we can also deal with high dimensional data more directly actually at the data level. And so reducing the number of dimensions in our data directly will also implicitly decrease our model complexity overall. So one way to do this is through feature selection methods. What feature selection methods do is they preserve the original variables that you have in your data set. What you're doing is actually selecting a subset of the total variables and eliminating the others. So sometimes these methods, they very often use recursive methods in order to select the different features that you would keep, or you might use statistical thresholds. And some examples of feature selection methods are things like recursive feature elimination, or using a chi-square test threshold, or the Boruta method. Feature extraction techniques are the other aspect of dimensionality reduction, a different way for you to reduce your dimensionality. What feature extraction methods do is they actually transform your original variables into new variables that are better suited for the modeling process. So examples of this might be applying word vectors or maybe applying clustering techniques to your data. You can be very creative often in your feature extraction methods, and sometimes they'll actually combine more than one. They'll combine more than one feature in the extraction process. And principal component analysis falls directly into this category. So I want to now talk more about the actual intuition and methodology behind principal component analysis. Why would you consider using principal component analysis? I've alluded to this quite a bit in the beginning, but the main reason you'd want to consider using PCA is that you want to ultimately reduce the number of variables in your model. But you could do that again with a feature selection technique, possibly just as easy as maybe something more complicated like PCA. So you might also want it to be, you also might want to be in a situation where it's not clear which features you actually want to eliminate. Sometimes it's very clear that certain features are essentially garbage or completely useless to your model, but you might not always be in a situation where that is so obvious. The next thing that you want to consider when running through sort of a mental checklist of whether or not you want to consider using principal component analysis is that you want to generate variables that are not correlated. So some models are fairly robust against correlated variables, especially certain ensembling techniques. But even some of these more sophisticated models can be a little bit difficult to interpret at the feature importance level sometimes, and correlated variables can sort of mask certain interactions. And then other models, such as logistic regressions, have this implicit assumption that the features are independent and shouldn't be correlated when you're modeling them. And then finally, you have to be okay with sacrificing some amount of interpretability for the potential downstream gains in the performance of perhaps a supervised model. because we're using a feature extraction technique, PCA is a feature extraction technique, you're not using the original variables in your model. So these new features that you're creating are going to be, by definition, less interpretable than the original things that you recorded. But they might be more useful for modeling, and that's the reason that you do them. And so you might have a better performance ultimately downstream when it comes to evaluating your models. I say potential downstream performance gains because PCA, you shouldn't think that PCA will automatically improve the performance of your model. If you have a couple features that are just very, very important in your model, doing a feature extraction technique is not really guaranteed to necessarily improve your performance overall. But in some circumstances, it can actually make quite the improvement. I have a schematic here of how you would introduce principal component analysis into a machine learning workflow. And what I really want to focus on is the data transformation aspects of things. I'm not going to go into how a supervised model process works. There's plenty of resources on the BigML website and other examples of how that works if you want to look more into evaluations and so forth. But in BigML, you would always start by importing your data set as a source and then converting it in as a data set. And in this example, I'm splitting my data set into a train set and a test set because I have in mind that downstream in this process, I will eventually be using a supervised model. And so using only the training data set, that is what I will use to apply my principal component analysis. Now, PCA can also be considered an unsupervised method, unsupervised machine learning method. So it's important when you build your PCA, you don't include the target variable, especially if you're going to be using this for a downstream supervised machine learning problem. Once you have this principal component analysis resource built in BigML, it's as easy as essentially applying a batch prediction or a batch projection in this case to your training and test sets. And it's important that you use the PCA resource built on your training set and applying that to your test set. And what this batch projection will ultimately yield are these new features for your modeling process and your evaluation process. So you'll have new training features and analogous new testing features that you can now work with. So what's so special about these new features? What do they represent? The new features that you get out of principal component analysis are the principal components. So you're essentially taking this original data matrix that we talked about, where you have instances as the rows in your data set, and you have different fields as the columns of your data set. And what we're going to now yield are new columns, which are our principal components. At this stage in the game, the number of dimensions in our transformed data matrix are exactly the same as our original data matrix. So these principal components if you have n original fields, you'll have n principal components. And so these are what the new variables are yielded by this. What the principal components are linear combinations of the original variables. So the first principal component will be some combination of all of the original fields, and so on and so forth for all n of your principal components. And so your question would be, how do you actually go and determine what those weights are? How do you make those linear combinations? And so I want to talk about a geometric interpretation of PCA to help explain how this works. Every data point, if you ignore the vertical lines just for the beginning here, this is from the classic iris data set, and what we have are sepal lengths and petal lengths plotted here as our two variables in this data set. And what PCA is going to do, it wants to find the direction in this data set that essentially explains the highest amount of variance. And what I mean, and what that actually is it will actually find the direction where the sum of these distances is at a minimum. So the greatest spread in the data set, which is about there, and I'll show you a static version of this so you don't have to imagine what it looks like spinning around. But when the sum of the normals here is at a minimum, that will indicate the direction where you have the greatest variance or spread in your data set, and that directionality indicates the first principal component. In this case, the direction of our first principal component would be essentially this line through the data here. And so you can see it indicates the greatest spread of the data along the axis, and you can see how that also is equivalent to the minimum distance of these points to the line. And then for each additional principal component, essentially what you do is you cancel out the effect of the first principal component, the direction of the first principal component for each ensuing principal components. So the second principal component would essentially be subtracting out this direction from the data set. And since we only have two variables in this data set, the next principal component would be in this axis. And you can see that these two axes will actually be orthogonal to one another or perpendicular. And that's a really important aspect of PCA, and it's why it yields uncorrelated variables. So that's the next point I want to talk about here. This is a different data set, but one of the most important properties of principal components is that you yield the principal components are not correlated, whereas your original data set may be correlated. So this is a different data set, but in this case, we have 15 or so different variables, and the intensity of the color here in this plot indicates how correlated. This is a correlation matrix showing how strong the correlations are. And so you can see there's definitely a few interactions that are very, very strong, and almost every variable is at least somewhat correlated with one another. There's like a very sort of light amount of color throughout this entire matrix. We can see in the transform data, all of these interactions are now gone. So principal components, any two principal components, none of them will be correlated with one another. The other important property of principal components is that they're sorted by the percentage of variance explained in the original data. So if we go back, if you recall the iris data set, where we're finding the greatest spread or the greatest variance, the orientation of the greatest variance in the data set, that is essentially it's trying to maximize the percent variance explained. And then for the next principal component, the first principal component has explained a good portion of that variance, so the next one will explain as much possible while being orthogonal to it, and then so on and so forth. There'll be sort of diminishing returns as we go to higher and higher number of principal components, whereas like in this case, there's 30 total principal components. If we were to scroll over, our 30th principal component would essentially be explaining almost none of the variance. In this case, our top principal component is explaining over 42% of the total variance. Our second principal component is explaining 20%, our third explaining 9%, and so on and so forth. And so what BigML provides in the dashboard, and I'll show you an example in more detail in a few moments, is a plot called a scree plot, which plots the cumulative variance explained as a function of the ordered or of the principal components sorted by their magnitude. And so it's very typical in a scree plot to have sort of this sort of shape to the curve where you sort of reach a threshold and it sort of levels out. And this is really important for maximizing essentially the amount of variance while minimizing the number of principal components you have to include. And that is sort of the secret sauce behind how you go and do dimensionality reduction. So if we look at the scree plot in a little bit more detail, there's essentially two different ways where you can reduce the dimensionality of your data set by selecting only a subset of your principal components to include. One way is to just directly select a number, for example here, 5 of the principal components you want to include. So in this case, if we go out to the fifth principal component, we can see on this plot that the top 5 principal components explain somewhere around 85% of the total variance in the data set. And so we can keep 85% of this variance, which is the important information essentially in the data set, with only 5 features rather than the original 30 features that we included. So it's a reduction of 25 features essentially that we're eliminating. Another approach to do this is to instead choose a threshold for the percent of variance explained that you want to keep. So in this case, we would say, okay, we want to have at least 80% of the variance explained by the top principal components that we'll keep in our data set. And in this case, it would also correspond to 5 total principal components. With that introduction, I now like to go and talk about and specifically show you a use case in the BigML dashboard. So here is our typical BigML dashboard view. And I've imported a data set of tumor data that we're going to be evaluating here. And so the first field in this data set is a diagnosis result. And so this can be either benign or malignant. Okay, so it's a 2-class classification problem that we ultimately want to solve downstream. And I have about 30 different fields here. And these are essentially measurements that were made of images of different tumors, specifically regarding the shape and size of the nucleus of these different tumors that were extracted. And so fields in this data set are things like the radius of the tumor. There's a feature for the texture of it, the smoothness, for example, its symmetry, and also like the standard errors of these different variables, and things like the minimum and maximum. So they've engineered lots of different features off of this. And you can imagine that a lot of these features are already correlated with one another. And so what we can do is we can look on the scatter plot and we can look at some of these most important features that we'd expect to, innately have a correlation with them. So things like radius, or let's say area and perimeter, we'd sort of expect those to automatically be correlated. And so what I can do here is I can plot the area versus the perimeter, and I can color in these points in this data set by the diagnosis code. We can see, again, they're very, very correlated with one another. You have a Pearson coefficient of higher than 0.98. And so this can be very problematic for lots of different models, having this high level of correlation between your variables. Even though there's some sort of separation here, we can see a bit of separation between the two classes based on these two features, but we could get at this in a more robust way using principal component analysis. And so how this will work is I'm going to go back to my data set, and what I'm going to do is I'm going to make a train test split. Because we ultimately want to apply this to a downstream supervised learning question. And so I'll quickly just rename these to make them a little bit shorter. And so I will yield my training data set, and it's important for in a principal component analysis type of workflow that I'm only going to apply the principal component analysis to my training data. If I apply it to the whole data set ahead of time, I automatically will have testing data leak into my training set and will bias my result. And so if you're looking for principal component analysis on the dashboard, you can find it under in the toolbar under the unsupervised models. So principal component analysis can be considered an unsupervised model because we don't want to include knowledge of the target variable in this case. And so if I go to configure a principal component analysis, I want to make sure that I deselect the diagnosis field. It's really important. I don't want this target variable to leak into my principal components. Essentially, if I don't select that field or remove that field from the principal component analysis, then the diagnosis will get a weight that's added into all my principal components. So now that I have all the other fields selected, what I can do is go ahead and create my principal component resource. And this will bring us to the view that I showed some screenshots of before, where we'll get a scree plot and we'll get our top principal components listed here. And so we can start inspecting some of these principal components. You can see like what the most important weights are. And so what's interesting about the first principal component here is that the highest weight is for the original field called concave points mean. The second most important field is for this, the second highest weight is for this original field called concavity mean. And the third highest weight is for a field called concave points worst. So principal component 1 definitely has a lot to do with concavity. I said in the beginning that if you're using principal component analysis, you have to consider that your results will be less interpretable. And obviously this principal component variable is going to be more complicated than these original variables, but it doesn't mean there isn't some level of interpretation you can make from it by actually going and exploring what the weights are of the most important variables in your data set. Very similarly, if we look at the top 3 weights for principal component 2, they all have to deal with fractals. So you can see fractal dimension standard error, fractal dimension worst, and fractal dimension mean. And then we can look at the scree plot here. We can see that our first principal component is explaining almost 44% of the total variance in the data set, and things start to level off pretty quickly. But using just the top 5 principal components, for example, we can explain over 80% of the data set. But for the sake of a slightly different example, let's say that we want to choose a dimensionality reduction that will provide 90% of the total variance explained. We could use the slider, or we could just type in the value here. And if I go to 90, this should yield the top 7 principal components. Let's see. And you can see that principal component 7 here corresponds to 90.98. So I'll actually just type in 7 here to make it a little bit more straightforward. And then I will create a data set from that. And so my new data set will not truly have dimensionality reduction in it because we're actually appending these new fields to our original variables. I will actually end up dealing with the dimensionality reduction aspect at the modeling time. So I can actually go and just choose, the top n number of principal components I want to include in my model, and ignore these others at the modeling end of this process. And so because I did this transformation to my training set, I have to go and do the equivalent to my test set. So what I'll do here is I will go into the PCA resources that I've created, and I can just go and create a batch projection really quickly. And then I will search through my data sets and choose my test set this time. And what this will yield is you can get a sort of a preview of the prediction file, but it will yield all my original variables plus all of the principal components that I want to have. And you can choose to configure this and limit it if you'd like. So I guess I could go and actually just do the top 7 here to make it equivalent. And so now if I look at my preview of my prediction file, I'll only have the first 7 principal components included here. And then I can give a name to this. So this will be my tumor data test with tumor data train. I'm just going to shorten the name very quickly and perform that projection. Now that I've applied the principal component analysis and perform the projection to both my training and test set, I can go ahead and model it with the principal component features rather than my original variables and see how that works out. And so I will go to my data set, which includes the PCA features, and I'm going to just build a logistic regression model. And it's important, and logistic regression is sort of a classic combination with principal component analysis because of this aspect of creating features that are all uncorrelated from one another. It allows logistic regression to perform better, essentially. And so I'm going to make sure my objective field is selected, but I'm going to exclude all the other fields of these original variables, and let's just only enable the principal component variables now for this prediction process and modeling process. So I'll create my logistic regression model. This will take just 1 second. We'll get back a list of the weights of how the different principal components, the different weights that were trained for this logistic regression model, and we can look at the probability based on different values for principal components. But what I really want to care about here is the evaluation of this model, and so I can go and evaluate it against my newly created test set with the principal component features. And I get back an evaluation now for a model using only principal component features. And so I've essentially reduced the dimensionality of this problem rather than using all of the features in my original data set. I'm only using a small subset of them based on this principal component analysis. And you can see the results in this case are very high. We have extremely high precision accuracy. Basically every metric is in the high 90s in this case. And we can look at, for example, the ROC curve if you prefer that visualization as well. We have an area under curve that's above a 0.98. That is sort of an example using only the dashboard of a quick and dirty workflow for a supervised learning problem where we engineer principal component features ahead of time in the process. And finally, just talk quickly about the BigML-specific implementation of principal component analysis. What we're referring to as principal component analysis is actually sort of an umbrella term for what's actually built into this functionality at BigML. So standard principal component analysis will only apply to numerical data, but BigML actually has 3 different data transformation methods built into this, what we're just referring to as PCA in general, that can handle all different data types. So for numeric data, we'll of course use the standard PCA method, but for categorical data, we'll use a very sort of similar approach or analogous approach called multiple correspondence analysis. And for mixed data, we'll be using an algorithm known as factorial analysis of mixed data. The take-home message here, what's most important about this is that BigML will essentially automatically handle principal component analysis and dimensionality reduction problems using PCA, whether your data is numeric, text, items, or categorical. And you don't need to provide any input about which one of these underlying transformation methods you want to use. It will automatically be able to detect the data type for a given field. And you can always have the ability to configure a field if something isn't reading it improperly, for example. If you're interested more about sort of the nitty-gritty of this implementation, you can refer to our most recent blog post which gives a very in-depth technical overview of how principal component analysis works. It's the sixth of a series of 6 blog posts that were released over the last 2 weeks that begin with a high-level introduction of principal component analysis, run through use cases, indicate how to use the dashboard for a different use case, as well as showing how to automate principal component analysis using the REST API or WisML or Python bindings.